Hello everyone, thank you for watching our presentation. I'm Rathijit. We will first give you a brief overview of AutoExecutor and then Abhishek will show you some demonstrations. Our goal is to predict the optimal parallelism for Spark SQL queries and allocate the right number of executors. This chart shows an example of how the running time of a TPCDS query can change according to the number of executors. Reusing terminology from prior work, we call this the performance characteristic curve or PCC. Similar to prior work, we model the PCC with a power law function to reflect its expected monotonic nature, but we also add a constant function to reflect a minimum value for the running time of the query. Our PCC model can thus be characterized by three scalar parameters, A, B, and M. Our approach is to use machine learning models such as random forest regressors that take into account query characteristics that are all available at compile time and optimization time, such as operator counts, estimates of total input cardinalities and bytes, number of input sources, plan depth, etc., and predict the query-specific values of the PCC model parameters. Here is an example of a PCC predicted by AutoExecutor for a query, and this is shown by the blue line. The green line shows the actual running times of the query with different executor counts, and the orange line shows estimates obtained from the Spark lens tool. But for Spark lens, we need one run of the query before we can estimate the running time of the query at other executor counts, whereas for AutoExecutor, we were able to predict the PCC without executing the query. This shows an overview of our system architecture. We use the Peregrine framework to collect anonymized plans and metrics from query executions. Then the workload analysis step updates the workload table with the query characteristics. The feature extraction step extracts feature values from the workload table for model training. The model training step also uses the PCC parameter values from the training data set as labels. The trained model is stored in a database. When a new query arrives, this model is retrieved and scored using the query characteristics, and then the right number of executors is requested. We will now show you some demonstrations of AutoExecutor model scorings.
Hello everyone, I am Abhishek Roy from Grey Systems Lab. Today I will present the demo of AutoExecutor on Azure Synapse. One of the major challenges for Spark users is to select the optimal degree of parallelism. It is difficult for the users to make this decision without knowing the relationship between the performance and the number of executors. In this notebook, we use performance characteristic curve to visually represent a query's runtime as the function of executor count. In the first demo scenario, the audience members can write any query over TPCDS tables in the notebook. For this demo, we are using TPCDS query 94. Let us look at the details of the analysis step. First, we featureize the query plan. Then we use the pre-trained model to predict the parameters of the performance characteristic curve and generate the points on the curve. Finally, we plot the performance characteristic curve. Here we can see that the performance flattens after 27 executors. Note that we did not execute the query even once to determine its performance characteristics. Now the users can rely on this notebook to manually pick the best executor count depending on their constraints. But we can automatically select the number of executors when the queries are submitted. We have extended the Spark optimizer with a custom optimizer rule. This rule can automatically select the executor count right before the performance flattens for the submitted query. In the second demo scenario, we can submit jobs using different executor selection techniques. Here is the executor usage plot with the online rule-based approach of AutoExecutor for TPCDS query 94. We can see that the number of allocated executors in blue line automatically increased from default value of 2 to 27 after we requested additional executors during the optimization phase. During the demonstration, the audience can compare performance with other executor selection techniques such as static learned feedback from past execution, dynamic allocation feature of Spark, and fixed selection. We'll show that the completely hands-free AutoExecutor approach provides better utilization and predictable performance compared to other methods. We have more demonstration scenarios such as using AutoExecutor with changing workloads and data sizes, and how performance characteristic curve can assist in recommending cluster configuration. Thank you for watching this demo.